Chapter 2, Principles of Machine Learning. At its core, deep learning is a class of machine learning models and methods. Hence, to understand deep learning, one must have at least a basic understanding of machine learning principles. There are dozens of general machine learning methods and models that one can cover, and our purpose here is certainly not to present a detailed account of all of these methods. Instead, we take a path that presents a general overview of machine learning and then focuses mostly on linear models, which are the most elementary neural networks out there. In the process, we explore gradient-based learning for the first time, a topic that plays a key role in the chapters that follow. In section 2.1, we overview the key activities of machine learning, including supervised learning, unsupervised learning, and variants of these. In section 2.2, we explore key elements of supervised learning. In section 2.3, we introduce linear models. These form the basis for many other models, as well as for the deep learning networks of this book. We then explore the basic gradient descent algorithm in section 2.4. Linear models can often be trained without gradient descent, yet exploring gradient descent in the context of linear models is a useful warm-up for the chapters that follow. In section 2.5, we discuss generalization ability, overfitting, and introduce techniques of regularization. We further discuss the training process, including splitting of the data and cross-validation methods. Most of this book deals with supervised learning methods. However, understanding basic techniques from unsupervised learning is also important. Hence, in section 2.6, we take a brief look at unsupervised methods, including k-means, clustering, and principal component analysis, PCA. In the process, we represent PCA as a simple example of an encoder-decoder, autoencoder architecture. Section 2.1, Key Activities of Machine Learning. The world of machine learning intersects heavily with both the worlds of statistics and computer science. In statistics, data and randomness are key. In contrast, in computer science, algorithms and computation are the focus. Machine learning borrows from both worlds and is about the combination of data and algorithms. It is all about training mathematical models on a computer in order to classify data, predict outcomes, estimate relationships, summarize data, control complex processes, and more. We now present and characterize a few key activities of machine learning. These activities are carried out when training, calibrating, adjusting, or designing machine learning models and algorithms. Many of these activities are loosely called learning, while other activities involve prediction or decision-making. Any activity of machine learning can be described as an interaction between the following entities: data, models, algorithms, and the real world. I'll say it again: data, models, algorithms, and the real world. By data, we mean collected data, such as the X, Y features label pairs described in the previous chapter, or data that is generated as output of models or algorithms. By models, we mean mathematical objects stored and implemented on a computer, together with the parameters that specify these objects. By algorithms, we mean the procedures for creating models, procedures for creating output datasets, as well as procedures for using the models themselves for prediction or related tasks. Finally, by the real world, we refer to scenarios that allow generation of data, annotation of data, as well as usage of output data for decision-making and control. Machine learning activities are often dichotomized into two broad categories: supervised learning and unsupervised learning. With supervised learning, data is assumed to be available as X, Y pairs, where each feature vector X is labeled via Y. In the case of unsupervised learning, one only observes data points X and tries to find relationships between the various elements, variables, or coordinates of X. To understand this terminology, Consider the learning of babies or toddlers, which only involves the exploration of input sensory data without any indication of what is what. This is unsupervised learning, since toddlers are typically not told explicitly, this does this and that does that. Then later on, for example, during school, they engage in supervised learning, since language and text are used to present the learners with examples X and their outcomes Y. A key activity in unsupervised learning is the usage of data. A key activity in supervised learning is the usage of data to learn or train models for prediction. See figure 2.1. This prediction is called classification in case the labels Y are from a finite discrete set, and it is called regression in case the labels Y are continuous variables. There are also other cases of prediction where the labels Y are vectors, images, or similar. A related activity is obviously to use the trained models for prediction when presented with unlabeled data from the real world. This is illustrated in the right of figure 2.1. We'll see the figure in a second. Both the training of models and usage of models for prediction involves the execution of algorithms. Sometimes the trained model is called an algorithm as well, since it may be integrated in part of bigger systems that use it. Most of this book focuses on supervised learning, and we begin in the next section, section 2.2, by overviewing key concepts of supervised learning. So let's look at figure 2.1. So in figure 2.1, we see supervised learning activities, and that includes training of a model and prediction of a model in production. So training data on the left-hand side goes into a learning algorithm, and notice that the training data has the features X and the labels Y. Okay. And the learning algorithm produces a model, and that's a prediction algorithm. We can call it, the model can be a prediction algorithm. And when presented with one set of features for one observation, say X tilde from the real world, the model gives a Y hat, which is a prediction. Now, of course, data from the real world on its own is also driving training data. Okay, so that this picture captures supervised learning. Okay, let's continue. With unsupervised learning, there are other activities beyond prediction, regression, and classification. See figure 2.2. We will in a second. One important activity is clustering, which focuses on finding groups of similar data samples. The output of algorithms that perform clustering are typically not considered as models, but are rather modified data sets that incorporate the clustering information. Another key unsupervised learning activity is to carry out data reduction, where high-dimensional vectors are transformed into lower-dimensional vectors that still encode some of the key relationships between variables. While unsupervised learning is not the focus of this book, several unsupervised learning algorithms are overviewed in section 2.6. So let's look at figure 2.2. So this figure captures two applications or two tasks in unsupervised learning. In one of them, in both cases, we have the input data, which just has features X. So that's the input data. One application or one task is a clustering algorithm, and another is a data reduction algorithm. Now, the output of these algorithms can either be a model or can be a transformation of the data. In the case of a data reduction algorithm, you could see that this transformed data X with the brev on top of it is of lower dimension, so it's thinner. In the case of clustering, we could see that there are clusters formed within the data. So that's an indication of unsupervised learning. Beyond the dichotomy of machine learning into supervised and unsupervised, there are also additional popular activities that aren't directly categorized as such. One popular class of activities is reinforcement learning, introduced in Chapter 8. in the context of deep learning. Here, a temporal component is key, and an agent is trained to carry out tasks in a dynamic environment. An additional class of activities is generative modeling, introduced in Chapter 8 in the context of generative adversarial networks and diffusion models. Here, models are trained to create artificial datasets with characteristics or a distribution similar to the input dataset. An additional suite of activities is transfer learning, discussed in Chapter 8 in the context of deep learning. Transfer learning is all about taking models that have been trained for one domain and adapting them to other domains with new data. Related is active learning, also briefly discussed in Chapter 8, in the context of deep learning, where the process is not static, but rather informed by the performance of the model on unseen data. This is very closely related to semi-supervised learning, also briefly discussed in Chapter 8. Here, like supervised learning, there are both feature vectors X and labels Y, yet only a subset of the feature vectors have accompanying labels. The learning process tries to use all of the available data. Finally, self-supervised learning, briefly discussed in the context of deep learning natural language processing in Chapter 7, creates models where sequences of data are used to self-predict the future or missing elements of the sequences. This is useful for language models and related tasks. Data: seen, unseen, training, and testing. Data is a central part of machine learning. In considering data, it is important to distinguish between seen data and unseen data. Seen data is the data available for learning, namely for training of models, model selection, parameter tuning, and testing of models. Unseen data is essentially unlimited, since it is all the data from the real world that is not available while learning takes place, but is later available when the model is used. This can be data from the future or data that was not collected or labeled with the seen data. Needless to say, for machine learning to work well, the nature of the seen data should be similar to that of the unseen data. The underlying assumption of machine learning is that the seen data used to create models is generated by underlying processes of the real world that are similar to the processes generating unseen data. Practically, one needs to design the data collection and labeling processes so that this resemblance between the seen and unseen data is maintained. A common practice in the world of machine learning is to split the seen data into training data and testing data. These are sometimes called the training set and the testing set. An additional name for the testing set is the holdout set. The key idea with such a split is to use the training data for learning and to use the testing data for mimicking a scenario of unseen data. As described in section 1.4, some popular example datasets come with such a predefined split. In other cases, it is up to the machine learning engineer to split the data randomly according to some predetermined proportions. Examples follow in this chapter. Since the purpose of the train-test data split is to mimic the unseen data with a test set, one should not recalibrate, adjust, or tune models on the training set while testing repeatedly on the test set. Carrying out such a repetitive use of the test set would invalidate its resemblance of unseen data. For this reason, one sometimes performs an additional split of the training data by removing a chunk out of the training data and calling it the validation set. More on this practice and other alternatives such as k-fold cross-validation is in section 2.5. The practice of splitting data into the train set and test set is very popular in machine learning so long as a large number of samples is available. However, in some cases, there is not enough data to be able to separate a testing set, and thus one wishes to use all available data for model fitting. This is sometimes the case when working with experimental data and biomedical data. In such cases, Statistical inference approaches for evaluating the quality of the model fit make heavier use of the model at hand. Some approaches for comparing models are likelihood-based and include performance measures such as the Archaic Information Criterion, AIC, or the Bayesian Information Criterion, BIC. The world of model fitting in a statistical context is vast, and we do not focus on such methods further in this book. Data pre-processing. Raw data often requires pre-processing before it can be used for training, prediction, or as input to other machine learning models. Although a full description of data processing steps and practical aspects of data processing is beyond our scope, one important activity that we cover is standardization of the data. This involves subtraction of the mean of each feature and division by the standard deviation of the feature. Assume the values for some feature I are x sub I superscript 1 for the first sample up to x sub I superscript n for the nth sample, where n is a number of data samples. The sample mean and sample variance of the feature are respectively computed as x sub I bar is the average of all the observations j going 1 to n, whereas the sample variance is the average of the deviations of these observations from the sample mean, summing again 1 to n. We have a footnote, footnote 1. In a statistical context, one often uses n-1 in the denominator of the sample variance instead of n. This is to keep the sample variance unbiased. For non-small n, this distinction is insignificant. So in machine learning, it's common to just divide by n. Further, the sample standard deviation is a square root of the sample variance and is denoted via SI. With these basic descriptive statistics of the feature available, we may standardize the data samples of each feature I1 to P to obtain standardized samples. So Zi superscript j, that's the jth sample for the ith feature, is the original data point, x sub I superscript j, minus the sample mean divided by the sample standard deviation of that feature. Now the standardized data for feature I, that's Zi superscript 1 up to Zi superscript n, has a sample mean of exactly 0 and a sample standard deviation of exactly 1. In the case of data samples of the feature, in the case the data samples of the feature are distributed according to a normal distribution, then most standardized samples would lie in the range -3, 3. Even if the data is not normally distributed, the standardized samples will still lie in the vicinity of this range and are centered about 0. Such standardization is useful as it places a dynamic range of the model inputs on a uniform scale and thus improves the numerical stability of algorithms. It also allows us to use similar models for different datasets that may, without normalization, have completely different dynamic ranges. In section 2.4, we discuss how such standardization can also help optimization performance. Learning approximately equals optimization. Almost any form of learning activity involves optimization, either explicitly or implicitly. This is because learning is a process of seeking model parameters that are best for some given task. In fact, all of Chapter 4 is devoted to optimization techniques in the context of machine learning and deep learning, and a few of the sections of this current chapter contain aspects of optimization as well. In some cases, optimization is carried out directly on some performance measure that quantifies how good the model at hand performs. This is, for example, the case when one considers the mean square error criterion for regression problems, a concept which we study in detail in this chapter. However, in other cases, a loss function is engineered for the problem at hand in a way that minimization of the loss function is a proxy for minimization of the actual performance measures that are of interest. This is, for example, the case when considering classification problems and aiming to get the most accurate classifier. In such a case, optimization is typically not carried out directly on the accuracy measure, but rather on a loss function such as a mean square error or cross entropy defined in Chapter 3. In any case, the design of loss functions as part of the learning procedure is central to machine learning and deep learning and appears throughout this book. Note that in some cases, machine learning algorithms, such as decision trees, do not directly specify an optimization procedure, but rather execute a predefined algorithm for fitting a model. However, even in such cases, there is typically an inherent hidden optimization problem associated with the procedure. Hence, in general, we can think of learning as a process of carrying out some sort of optimization. Okay, so this concludes section 2.1. We hope you found this useful. Let us know what you think in the comments below. Thank you.